Hello and welcome. Thank you for joining us for the Consulting Specifying Engineer webcast, Critical Power, Backup, Standby, and Emergency Power in Mission Critical Facilities, sponsored by ABB and ASCO. I'm your moderator, Amara Rozgis, with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you during this hour-long education session. Let's learn more about this platform. If you're having trouble with your slides or the audio, refresh your internet browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen and do some system checks before contacting an online technician. If you do need help, please type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, click on the Event Resources on the left side of your screen. Please type questions for our presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation. The interactive Q&A portion will begin in about 45 minutes. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab on the top of your screen. The quiz will open in a new browser window, so I recommend you open the tab right now because the link will break when the webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. Thank you. These are the learning objectives for today. We'll talk about these in the presentation. Please note that any red underlined text you see is a hyperlink within the PDF where you can get more information. Now let's hear from this session's sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for different internet speeds. Please stay tuned after the videos for today's presentation.
We know that safety is always a top priority. Are you keeping up with the innovations helping to make safer power distribution possible? From the largest piece of arc-resistant switchgear to the smallest arc fault and ground fault sensing circuit breaker, ABB is designing ways to help lower the risk of harm to both people and equipment. A forgotten tool inside the enclosure is a common cause of arc flash. Reduce the risk of a tool coming in contact with the bus stack or breaker connections with ABB's IP20 certified bus stack. Help enhance operator safety with groundbreaking T-Max XT circuit breakers. Remote metering and monitoring allow users to access information anytime, anywhere. With support for over 10 communication protocols, you'll always be connected to what's happening in your power distribution system. Optional Bluetooth connectivity allows personnel to set parameters and check measurements directly from their smartphone, all from an arc-free zone. Accessories like reduced energy let-through modules help to further enhance operator safety. And surge protection devices and advanced voltage and frequency protections can help prevent power quality issues from damaging sensitive equipment as well. Work safer and protect your assets with innovative design.
Very nice. The support is definitely appreciated. We have lined up two really wonderful presenters today. First, Brian Renner is a principal engineer and the mission critical leader at Smith Group, where he has 30 years of experience as a manager, director, and engineering leader in the design of numerous types of facilities. He has a passion for mission critical and science and technology facilities. He's a longtime member of the Consulting, Specifying Engineer Editorial Advisory Board and has been contributing articles and presentations for many years. It's great to have him as a repeat presenter. Zachary Carter is a senior electrical engineer at IMEG Corporation. His background includes project management and electrical design for the private and federal healthcare and commercial and government sectors. Zach's electrical engineering experience includes lighting design, power distribution, emergency power systems, and fire alarm systems. He also takes great interest in participating in the fast-track project delivery methods that are being seen in the built environment. All right, well, I'm eager to get started on this presentation. Zach, you're up first. Let's begin.
Thank you, Amara, and happy to be here with everyone today to learn a little bit more about mission critical facilities and help better define that for all the listeners out there. So start things off, I encourage everyone to take a moment to think about what mission critical means to you right now. Naturally, you're probably considering different types of projects that you design each day, or perhaps even a client that you commonly interact with. And your thoughts might even take you to say, well, it depends. It depends on it depends on how I define mission critical. So for many campuses and facilities, defining mission critical does depend. During utility power outages, mission critical facilities rely on generators to keep the facility operating. And if the generator were to fail to start, or if there's a fault in the power system, the facility will eventually stop operating. So the layers which the generator and the electrical distribution systems are designed will define the criticality of the mission. So mission critical can be more simply defined as a facility that is essential to the survival of a business or an organization. So mission critical facilities are significantly affected when the power is interrupted. So there's three key things that I like to think about when we talk about mission critical facilities that you'll hear, and it's availability, reliability, and security. So availability being when a system is called on to operate, it must be available to start and maintain operation. And reliability, meaning that if a power system should fail, it should be able to recover to the next level of redundancy. And the last year we have the security, and what I like to think about here is physical security, such as does a natural disaster impact the availability, reliability of the system, and if so, perhaps there's some security measures that should be taken. So we'll develop into the different layers of what mission critical means over the next slides throughout the presentation. So where mission critical is more solidly defined would be the healthcare and data center applications, along with the critical operations, power systems, which is Article 708 of the National Electrical Code. So I wanted just to point these out to where if somebody says mission critical facility on a public or private facility, more times than not, they could be talking about one of these three things, because these are three of the most, I should say, well-defined in standards of code that we have throughout the industry. However, I want to make it known that mission critical facilities aren't limited to just public or just private. It is certainly both. So before we proceed into more details of these types of facilities, it's important to know the systems and the codes that we'll commonly encounter. So with that, I'm going to hand it over to Brian to talk a little generator basics.
Thanks, Zach. So we've gone over what could be considered mission critical. We want to go over a little bit of the generator basics. So as we're talking throughout the rest of the slides, you understand, we call them generators. They're listed here as generators, but really they're engine generators. There's two major components, that is the engine and then the generator that puts the electricity together. There's also radiator, battery, circuit breaker entry, controls. All of those things go into the generator as you're specifying it and looking at it. Some things to note that are not shown on here, and we'll talk a little bit later about them, especially on indoor applications. You're not showing here the exhaust silencer muffler treatment. There are EPA tiers we could get into a long discussion on, but many localities are requiring significant reductions in emissions from these generators, and the exhaust silencers or mufflers or treatment that go above these generators can be quite large. And Zach will talk about that a little bit later as we talk about some of the architectural issues. The radiator can also be located at the generator or remotely if it's inside a building, because these require significant amount of air when you're trying to cool and run a generator. The other things to note when we talk about the generator and alternator is that the generator manufacturers will typically specify a standard package of a generator and an engine together, and you have options to look at those differently depending on your load profile, and we'll talk a little bit more about that in a little bit. So let's get into the codes. Zach?
All right. Thanks, Brian. So I thought it'd be important to mention the 3 regularly referenced codes that you're going to run into for mission critical facilities in all systems that you'll design. So we have the NFPA 70, which is the National Electrical Code, NFPA 110, and NFPA 101. And I just want to highlight a few things on each one of these codes. Excuse me. So the National Electrical Code contains requirements for the generator emergency systems, again, for both the public and private facilities. For most generator applications, you'll be encountering Article 700, 701, or 702. That'll be kind of the first place to start when you're looking at a mission critical facility. I'll break those down a little bit further in the next slide. You also have Article 517 within the NFPA 70 National Electrical Code, which is used for healthcare facilities, and also has requirements, and that's tied into more healthcare specific things that we'll dive into even later. NFPA 110 is the standard for emergency and standby power systems. So this is this relates to installation, testing, and maintenance of emergency generators. And so with this, the 3 things that are most important for the NFPA 110 for your mission critical facilities is the type, the classification, and then the level. The type defines the maximum time that the load terminals of a tracer switch can be without acceptable power. And then classification is another level. That's the minimum operation time at full load without having to be refueled. And then the level determines the installation, performance, and maintenance requirements of a system. Typically, there's a level 1 system or a level 2 system that are defined. The level 1 could result in the loss of a human life or have serious consequences or serious injuries, and level 2 is less critical. A standard designation that I like to always give out there is if you were to look at NEC Article 700 and just see what the minimum type, classification, and level would be for an Article 700 system, which we'll talk about in the next slide, would be a Type 10, Class 2, Level 1 system. So Type 1 being this is going to come on within 10 seconds and deliver power to the load terminals of the transfer switch. Class 2 for a minimum operating time of 2 hours, which if you think about the emergency system, 2 hours to get people evacuated out from a space, that seems to make sense. And then level 1, meaning that if the failure of the system were to occur, there could be potential loss of human life or serious injuries. So Article 700 is Type 10, Class 2, Level 1. And then if you, for those of you who might be a little more in tune with NFPA 110, you will run into what is a Class X, which you'll see on mission critical facilities. So the best example I can give there is that healthcare facilities usually fall within Class X, where X is determined, the amount of time X is determined by other codes for state adoption or runtimes. And then the last one that ties into the basics on the regular reference code is the NFPA 101 Life Safety Code. And so this defines the requirements for the illumination means of egress and exit signs that are tied back into the National Electrical Code and the NFPA 110. So doing a little bit deeper dive into the National Electrical Code, NFPA 70, I really want to point out these different articles, Article 700, 701, and 702. And you see 708 here, which I'll briefly touch on. So you'll have the emergency systems, which is Article 700. So this system that's defined in the NEC is a system that's intended to automatically supply illumination and power to designated areas, and it's essential to human life. So we're talking about safe exiting or panic control in large buildings. Other systems, these also may provide power for is ventilation or fire detection systems, alarms, elevators, fire pumps. And so this system is, another thing to note here is that these systems are supposed to come online within 10 seconds. And I should define what come online means in case I use that throughout this presentation. When I say come online, it means generator start and deliver power to the load terminals within that 10 seconds, just like that type was defined in FPA 110. Legally required systems is just maybe a tier down from the emergency systems. So these are systems that are intended to automatically supply select loads other than the emergency systems in the event of a failure of the normal source. The best example that I can give for a legally required system is a project that I've done recently down in Florida, where we had multiple branches, 700, 701, 702. So I had my 700, which was my egress lighting and things that, again, get folks to egress safely out of the building. But then I had this lift station that was for the wastewater within the facility. So it didn't make sense that that was on the emergency system, and it definitely wasn't an optional system. So that's where it fell right into that legally required system for Article 702 there. And those are to come online within 60 seconds of the generator starting. So then we have Article 702, which is the optional standby systems. These are systems where the life safety doesn't depend on the performance of the system. So this is a great example for what we're talking about today, mission critical facilities. It's beyond the emergency, beyond the legally required for what does the client or the owner of the facility want to have continue to be operational beyond the utility outage that has everything to do with their operation of their facility, whether it's an industrial building or commercial building. So when these loads are stopped, it affects the operation of their business. So while the branch in Article 702 it says optional, it by all means may not be optional to what they perceive for their business. Per code, technically, these are not required to start automatically, although that is what we commonly see. And this last one here is the Critical Operations Power Systems NEC Article 708. So when we talk about public mission critical facilities, this is the best example that I can give. This is if you're designing a project with an emergency operations center or a 911 call center for a public entity, a county or a city, more times than not, the systems that you'll encounter would follow the requirements of this NEC Article 708. So with that, on the National Electrical Code, Brian's going to give us a few updates in regards to some 2020 updates.
Thanks, Zach. So I'm just there's a lot of updates in 2020, but I'm going to focus right here on Article 700 on the emergency section for emergency generators. There wasn't a ton actually this revision. There were some significant ones in the previous editions. But one of the things they added in 700.4 was capacity. They added and rating. One of the things you need to know, obviously, as an engineer is you're not just dealing with a 1,000 kW generator, but you're dealing with a 1,000 kW generator that can adequately handle the types of loads that you're going to have in the facility, and the generator rating itself is appropriate for the situation. We don't have time to go into it, but you'll notice when you're looking through cut sheets from the various generator manufacturers, they have emergency standby ratings, they have a continuous rating, prime rating, and even data center ratings. And these all talk about how much capacity you can put on that rated generator and for how many hours it should run. So be aware of that when you're looking at the rating of your generators. And we're going to talk a little bit later about some of the issues with loading and load studies. 700.12 separated out duration and location. Zach mentioned about the class X or the duration. What the NEC does is it doesn't put in specific times in its code, but it does tell you that you have to look at the specific hours necessary for in an emergency situation for people, for the building to function and evacuation example, or loads need to run. Evacuating, a medium-sized office building may not be the same as a 2,000-seat stadium. So durations are important for you to look at, and that we'll talk about fuel runtime later. And also the location. In certain things, high occupancy locations have extra fire protection, have to be located in a way that makes them more reliable for an emergency application. And lastly, there's been a lot of discussion lately about microgrids. 700-12 talks about microgrids and the fact that, no, you cannot use your microgrid if it is the primary source of power as also your emergency source. However, in most applications, the microgrids are providing supplementary power to a campus or a building and not the normal source of power, in which case those microgrids can be used as an emergency source when they're not the normal source. And at this point, Amara would like to take a survey.
Excellent. Thank you, Brian. All right, we're going to do a quick poll of the audience. We're talking about mission critical facilities here, but we want to find out what you're working on. So if you could answer this question, what is the most common building structure in which you specify, design, or make product selections? So I'll give you a few seconds to take this poll. We are looking at a lot of different building types here, and many of them could be considered mission critical, whether it's a bank or financial institution. I think most people would lump something like a data center into the term mission critical, but we want to find out what you're working on. So let's see here. Results are still coming in. It looks like a lot of people are working in hospitals and healthcare facilities. We have about a quarter of you working in hospitals and healthcare, and let's see, about 20% in data centers. And then we've got several folks working in public works facilities or municipal facilities. So we're going to target a couple different building types. I see here that data centers and hospitals look like they are the highest. So let's move on and start talking about those.
Okay, thanks, Amara. So we're going to take a deep dive into healthcare facilities, as they're one of the more important mission critical facilities that we encounter. So to set the table with the healthcare facilities, it should be noted that healthcare facilities include many different types of facilities, and they're not just limited to hospitals. Dental facilities, nursing homes, ambulatory care centers are some good examples. And it's also important to remember there's a difference between healthcare facility and then a healthcare occupancy. Not all healthcare facilities are considered healthcare occupancies. Perhaps within the hospital, there's that business occupancy, assembly occupancy, or storage space as well. So I'll touch on a lot on the codes and standards, but bear with me. There's a few more for the healthcare. It's again, it's one of those more clearly defined mission critical facilities, so this is important. We have the NFPA 70, Article 517, which gives us criteria for healthcare facilities. And that aligns a lot with the NFPA 99, which is the Healthcare Facilities Code. And those Article 99, or NFPA 99 and Article 517 of the NFPA 70 there's been a lot of effort over the past few code cycles to create alignment between those for any of the healthcare designers out there. That's something good to note. And then we also have the Facility Guidelines Institute, which has requirements for healthcare facilities. And then I always like to mention the Joint Commission and then the CMS, the Centers for Medicare and Medicaid Services. Of course, they inspect the facilities for compliance of the codes and the standards. And the hospital needs to meet these codes and standards so that they can be reimbursed properly for services that they provide. So get into a little more fun stuff, showing a one-line diagram system here. Try to color code it, maybe to follow a little bit more easy for us out there. So the redundancy and reliability for an electrical distribution system doesn't just start on the generator side, but it also starts on the normal service as well. And so the normal service, which I'll get into the very next slide, it can be made as reliable as possible, which in many instances can be just as classified just as with the same level, or excuse me, it could be classified with a greater level of redundancy when you have the multiple sources on the normal side. But overall, when we're designing healthcare facility or mission critical facility, we're trying to minimize interruptions. That's the goal. We're looking for near normal operating conditions when they're operating on the normal, obviously, and then when they're operating on the generator. So when it comes to healthcare systems, our NFPA 99 is going to have us follow different category levels. So for a critical care, NFPA 99 defined critical care category 1 space. It requires these 3 different colored transfer switches. This is the transfer switch arrangements that they prescribe. And so we have the life safety, critical, and the equipment branches. So taking it from the colors, the green is showing our normal source with the normal local utility power would come in from, and then if those were to be lost, then we transfer to the life safety, critical, and equipment. The pink, or the life safety codes, or excuse me, the life safety loads can be defined as the egress illumination, fire alarms, emergency communication systems, elevator cab lighting, automatic doors. And the critical loads here shown in orange, I like to think these as patient care. These are nurse call systems, receptacles for patient beds, ICU units, operating rooms, and even another load that's under the critical branch is the telephone rooms and closets. And at first I always kind of struggled with this, kind of understanding why would we want the telephone rooms and closets and the equipment on there. Well, think about how much technology systems are involved in today's healthcare systems. So I would definitely consider these as patient care or critical loads for that system. And the equipment branch here that I've shown in blue for the transfer switches, these are primarily 3-phase mechanical loads. So here we're talking vacuum systems, sump pumps, HVAC equipment, smoke control, and stair pressurization equipment. So I want to add a little bit of redundancy to the code minimum required healthcare or essential electrical system, I should call it. So I can do this in many ways. So on this example, I just wanted to point out, again, on the normal side, right, you can have multiple normal services, which creates another level of redundancy that we can get from the utility. And you can also have multiple generators, one that can be paralleled for more redundancy. On the normal side, you can have a main tie main arrangement with a main breaker, a tie breaker, and another main breaker on an A and a B bus, or you could have a primary reserve system on the normal side. So as you're creating, for mission critical facilities, as you're creating these levels of, let's call them layers, right, with the 2 normal services and these 2 generator services, it's very important to understand just that security aspect that we talked about in the first slide. Make sure we're keeping the separation of these, physical separation of these different feeds as they enter the building and distribute throughout the space. Best example I can give is 2 normal utility feeds into a main tie main arrangement, and then we have a duct bank that goes and distributes to a campus. If those arrangements were to be within the same duct bank and the same manholes, should there be a fault or an interruption in the manhole, would that take out both normal services and have greater, basically your reliability is for nothing. All the levels that you built upstream are for nothing if you have an issue, because you have basically you're taking 2 birds with 1 stone, if you will, with a fault in the manhole. Next thing I want to highlight here is what some folks might know, or some folks on the call might know, is ride through. So with the utility to generator transfer, there's going to be an outage, if you will, or delay. So there could be some loads downstream. I'm sure Brian will get into this into his slides later on, but there'll be some loads downstream that you can't even see a blip. You don't even want an outage. So the best example I can give on healthcare is imaging equipment loads, CTs, X-rays, or any radiology rooms. An MRI, for example, could take up to an hour for one of the images. Should that image be lost because of an outage, perhaps that has some catastrophic scheduling issues with the hospital. They have to push back dates and push back dates and push back dates. So investing in a UPS or uninterruptible power supply could ride through that normal to generator source, which we're seeing more common on a lot of imaging equipment loads and even computer system loads. So with that, I'll hand it over to Brian.
Thanks, Zach. So I noticed there was a number of people on the call involved in data centers, but I think there's an interesting example too of the use of generators for mission critical that are other than legally required standby or emergency. Yes, there are emergency and maybe legally required standby loads in a data center, but most of these are considered optional backups under the code. But that still doesn't mean that they don't have to have the requirements that we would like to have with 10-second startup times and reliability that are with emergency. So let's talk about who uses data centers. I mean, the one that commonly comes to mind, obviously, is the big data centers you see for some of the enterprise data centers, the social media companies, the internet companies, that type of thing, the internet providers. But there's another use, the difference between enterprise. There's cloud and co-location. You probably hear a lot about the cloud, and you may hear less about co-location. But basically, those are facilities where you either decide to have the equipment and the data center provided to you. That's the cloud. You're leasing their telecom equipment, their computing equipment in a space that they own, and they own the equipment as well. A co-location data center is one where you will put your data center equipment, because maybe you can't afford to maintain one or build one, but you'll put your own IT in a facility that has generators and power available for it. Direct end users besides the enterprise would be finance and insurance companies are big users of data center. But everybody's using data centers these days. Universities, certainly just for all of the functions and data they need to process, but also for research, as well as the government also using them for research. And we're going to talk in just a second about research computing and what the difference between what we consider high performance computing and standard data center computing environments. So let's look at two examples, hypothetical examples. One is a 200,000 square foot co-location facility. Maybe it's multi-story data centers are a big deal these days, so maybe it's a 3 or 4 story data center. In this, we usually measure power demand by kilowatts per rack. So you might have 10 to 20 kilowatts per rack in a standard co-location, even in an enterprise or social media company. So for this 200,000 square foot data center, you could have a total site power required of nearly 25 megawatts. That's a lot of power. Data centers take a lot of power, and they require a lot of generators to keep that power going, not only for the equipment, but for the cooling as well at times. However, if we take, say, a look at a 100,000 square foot high performance computing facility, what used to be called supercomputing projects, and you can see a picture of a supercomputer, artificial intelligence computer there in the slide. Those can have up to 200 kW per rack. That's kind of cutting edge. Most of the high performance computing might be in the 60 to 100 these days, but we're working on projects as high as 200 kW right now. So for that 100,000 square foot facility, you might have the same or more power than you would for a double-sized data center. So when you're looking at the amount of power, the amount of generators you have to put in, it matters. But the thing about research computing is typically they require less generator backup than a co-location enterprise type that has to run continuously operating. So the amount of generators that you might put in would be different. So let's talk a little bit about standards rather than codes. One of the most frequently used standards for data centers is the Uptime Institute, which classifies 4 tiers for data centers in terms of their reliability, availability, maintainability. And we'll have a slide in a minute about that. But basically goes from the most basic tier 1 up to tier 4, which is the most fault tolerant of the designs. We'll show that table in a second. The other standard that's out there for electricals is ANSI TIA 942, and you can look up that link. Okay, so here's a little table of the Uptime Institute tier ratings, very common in the industry. You can see there the tier 1 to tier 4 being the most rigorous. It comes down to things like the number of redundant paths, how many, whether it needs continuous cooling, whether it needs redundant or multiple generators, N plus 1, 2N, in terms of backup and redundancy and concurrent maintainability. So there's a whole standard here with how these are put together. What you find is that there are some data centers that rigorously follow these tiers, and they actually go through the Uptime Institute certification. They cannot officially claim a data center as a tier 2 or tier 3 without going through that certification. What you will find, though, is that many of the data center operators will tell a designer, I want tier 3-ish, close to it, but they'll take some not exact requirements, but close to it for those. So you have to look at that closely and discuss with the client what level of reliability they're getting into and really what amount of uptime and concurrent maintainability they want. So let's take a look at a couple of sample designs of a generator. In this case, you've got two medium voltage sources to a site. And you've got that N plus 1 generator. In this case, rather than putting a generator for each data center hall, they put what's called a catcher generator. This is a simple way to not have a generator for each hall, the data hall, but use one for multiples. They also separate out the mechanical loads from the IT loads, which is important for power quality and reliability. Okay, you can do, Zach mentioned parallel generators. In some applications, particularly high performance computing with a high density, you can parallel generators. This allows you more capacity and allows you to simplify operations without having multiple smaller generators. So let's, Zach and I, get into best practices.
All right, thanks, Brian. And I think tailing off your data centers, Brian, in healthcare facilities sometimes, right, we have some data centers, right, we have those computer rooms. And so I think just from my experience, we run into some clients sometimes who will use a lot of the data center terminology or data center standards or references. So I think it's always important to kind of, either as a healthcare designer or as a data center designer, I always think it's important to have a good feel on both of those codes and standards, because more times than not, you have to guide your client through and navigate your client through many different layers of codes and standards. So I always find that interesting when somebody says they want to tier something data center within their hospital. It's important the designer has a feel for what that means. So like Brian said, going into different best practices regarding design and specifications. So a term that you've heard us throw out quite a bit today is our automatic transfer switches, which are essential for proper operation of your mission critical facilities. The example I wanted to show here is, and point out here, is that the quantity of transfer switches will be impactful. And the reliability of the system can be increased with the number of transfer switches. And this is essentially because you're isolating the certain loads to a certain transfer switch at a given time. The example in the transfer switch schedule I wanted to pull up here, it just shows a life safety or critical and equipment branch transfer switch. Again, this is that essential electrical system that I was describing earlier. Typically we'll have, or we will always have, the priority column, the priorities 1, 2, and 3, because with the different layers of the essential electrical distribution system, the life safety loads need to come on first before the critical, and the critical before the equipment. So that's the priority groupings are for it. And then we have the multiple types of transfer switches more times than not automatic transfer switches are specified on the mission critical jobs. A couple other points regarding transfer switches. Load shedding or load sequencing, you'll hear a lot, right? If let's say that we have a generator where we're needing to take loads off of the generator because we need the generator to carry some loads a little bit longer, or simply the generator is getting overloaded, we'll specify a transfer switch with the ability to shed the load off, or load sequencing or load stepping. It would be vice versa in case we need to step load, or we realize that we have more capacity within the generator, we can add that optional branch on the generator. We have load sequencing or load stepping transfer switches. And then another consideration too is the make before break or break before make transfer switches. Some folks on the call might know these as closed transition or open transition transfer switches. Closed transition is the make before break. We see this a lot in the healthcare facilities where they're making both the utility connection and the generator connection to the load terminals for a very small amount of time. We're paralleling those two sources. So we're making before we're breaking into the other source. So it's a closed transition. And the reason we do that is to eliminate or prevent some of the nuisance blips, if you will, from the transfer. The only issues with the closed transition transfer switch are that you need to work closely with your utility company because you're paralleling with their source that you're feeding the building. So closed transitions, or also known as make before break. I think the key thing to remember there is coordinate with your utility company and their requirements. Opposite of that would be the break before make, or the open transition transfer switches, which there's a clean cut between the normal operation and the generator operation. Selective coordination. Three things that we can pull from code in regards to selective coordination is the emergency branch, legally required branch. These have the overcurrent protective devices throughout the system must be selectively coordinated. This is essentially the domino effect. Any mission critical facility that we encounter, we don't want a downstream domino, if you will, take it up the upstream, which then takes out the entire system. So I want to point out these three particular code sections in regards to selective coordination. And then moving on to some more best practices, some of that physical security that we talked about earlier is, again, we've got two normal feeds, two generators, we've designed a beautiful system. Well, don't let the Achilles heel be the physical security or the location of the generator. Best practices that we see are to locate generators above a 100-year floodplain. Article 708 tells us we must do this for those public entities, for those critical operations power systems. And it all boils down to making sure we're locating that generator array away from high-risk areas, so we don't have history repeating itself with one of the hurricanes, Hurricane Katrina, Hurricane Sandy, where many folks had generators, but when they were called to start, could not. So, Brian, go ahead.
Thanks, Zach. So let's talk a little bit about sizing considerations. Again, this could be a whole topic in of itself. One of the things to note that I learned early on as a young engineer is that generators are kW limited. While most of us understand what the power factor might be for a facility we're designing, in most cases it's going to be pretty high, 0.9 or higher. Really, the old kind of industrial facilities or older facilities might be at a lower power factor. The generators themselves remain at a 0.8 power factor. So when you're looking at the kW/kVA ratings of the generator, I would encourage you to focus on the kW rating and skip the kVA, just a rule of thumb, until you've done your full load study. You have to look at the demand and diversity. Obviously, under emergency, Article 700, you have to use the 100% load. When you get into things like optional or data centers or that type of thing, you can start to look at demand and diversity calculations to reduce the size of the generator to the anticipated actual load. You have to look at the starting. What kind of loads are you going to have? Are you going to have large motors? Are you going to have a fire pump? Hopefully, you're dealing with your fire protection engineer and asking him to put a reduced voltage starter or variable speed drive on the fire pump to limit the amount of inrush current that happens to the emergency generator when that fire pump starts up. And also often looked in load starting are transformers. If you have a generator, we had some questions about medium voltage. If you have a generator feeding transformers, those also have high inrush currents. So if those transformers are coming online and hitting a generator after an outage, they're acting a little bit like motors in terms of their needs. The UPS systems gotten a lot better over the years. In the old days, they used to tell you make the generator 2 to 3 times the UPS. It's because UPS had poor electronics and input harmonics and issues. These days, they're pretty close to unity power factor in terms of how the generator will see them. But you do have to look at the amount of UPS systems, and you might have to do things like stepping the UPS on or some other options. Site altitude and temperature can affect the generator. Make sure you know if it's located outside, what temperatures it will be exposed to, what the site altitude is, and work with your generator supplier to help pick the right rating for the generator. And last thing, almost all the major generator suppliers offer free sizing software, either online or that you can install on your PC. Make use of that vendor sizing software as early in the project as you can when you start to get the actual loads from mechanical and the client on what's going in. It's really important to run those calculations. Zach talked a little bit, and so did I, about paralleling. This has gotten a lot easier in the last couple of years. In the old days, you had big switch gear, all these relays. It was kind of clumsy, and the controls were slow. These days, it's a lot faster. The electronics, the generators themselves have paralleling controls. They can all talk to each other without having going back to a large gear, although you can still have the paralleling gear with all the relays and the logic and the controlling. A lot of times you can just have the generators handling that paralleling, and the gear becomes kind of a dumb gear for the generator collective powers. It's a nice way to do redundancy, to have, say, 3 smaller generators instead of 2 big generators, so that there's a ability to have an N+1 arrangement. There's still concern about startup time, particularly among the older AHJs in the field who are used to the older paralleling systems. So make sure you work with your generator vendor to talk about those concerns on startup times. We've had several instances where these definitely can come on in 10 seconds or less, but we still end up doing a phased step load onto transfer switches to separate out the loads. Testing is really important for mission critical, for any time you're going to use a generator for a facility, but particularly mission critical. There are a lot of different tests. There's factory tests. If you can, it's great to go see these, witness test them as the engineer or owner at the factory before they're shipped. There are on-site tests that can be performed with the supplier of the generator or with other professionals. One of those on-site tests is called acceptance testing, and it's covered under the NETA standard. They basically check all the wiring, every kind of detailed test or an inspection that you might want on switchgear and generators. You can also have the commissioning done, and you should have commissioning done. It's almost mandatory on any mission critical facility, where it's more of a functional testing, where the systems are put through their paces, the design document and the basis design is reviewed. And then there's periodic testing under NEC and NFPA for load banks, and that is specified how often and how much load you have to put on the generator. Turn this over to Zach on our architectural coordination.
Thanks, Brian. Yeah, we wanted to cover indoor space considerations and outdoor space for location of your mission critical generators. Indoor spaces, room heights are concerned. We also need to consider, it might be easy to install it day one. Contractors have the right tools and equipment and its space correctly, but we also need to be thinking of how we're going to remove that or replace that in the future. Also, how are we getting around the space, and louvers for intake and exhaust. coordination are important as well for indoor generators. Moving on to the outdoor spaces, there's a couple different design types for the enclosures. You can have a skin tight or skinned, typically available up to 500 kW, and also some custom walk-in enclosures for outdoor generators as well. You know, I think the thing with outdoor generators, again, that physical security space. You maybe don't want to put this out in the middle of a parking lot where somebody could run into it, or you might want to conceal it architecturally. So certainly, there's pros and cons of both the indoor location, the outdoor location of your mission critical generators. We're hoping to highlight a few to consider for either scenario, indoor or outdoor, for you here on these slides. And then, Brian, I think you're going to talk a little bit about the current and future trends.
Yeah, so we're seeing a lot of push for alternative solutions to generators. Generators have been around for a long time, right? But there's concerns about sustainability, emissions, noise, those types of things. So there's been a big push in the last couple of years with large-scale utility battery systems. I'm sure you're familiar with one of the major names in battery systems. But those are being looked at more and more, particularly as some data centers say, we don't need to be tier 3 or tier 4. Maybe we can be tier 1 or tier 2, and we don't need, you know, days of backup, or maybe we want to rely on the batteries. There's these large scale batteries. Fuel cells are turning up as a future, going to hit the market more and more as an alternative to generators. Microgrids. How can we use all this installed backup power that we're putting or need on a site and make this a way to generate our own power and do it in a sustainable way? And with regards to those two things, there's a lot of push these days about alternative fuels. You hear a lot of talk about hydrogen. Hydrogen, depending on where it's sourced from, there are different types of hydrogen, can be very clean or dirty hydrogen. But that's a great way that some of the generator manufacturers, particularly natural gas generators, are being made now to handle a blend of hydrogen and natural gas. There are also hydro-treated vegetable oils that are out now that are better than the old biodiesel that can run in diesel engines. So there's a lot of discussion and push for alternative ways to back up mission-critical facilities. And with that, I think we are concluded.
Yes, we are. Thank you both very, very much. I wanted to remind you that you can earn one AIA CES approved learning unit. Just go to the Learning Unit Exam tab at the top of your screen. And while you're preparing for that, we have been preparing for questions. Please type your question into the Ask a Question box and type the presenter's name before your question so I know who should answer it. We'll get to as many questions as time allows, and questions that we do not get to will be posted at www.csemag.com. And to download those presentation slides, you can do that under the event resources on the left side of your screen. All right, gentlemen, we have a lot of questions here from the audience. Brian, I'm going to give the first question to you. What facilities are considered mission critical?
Okay, so Zach did a good example. Obviously hospitals and data centers, but we're seeing more and more owners define what is mission critical based on their processes, what it costs them when the power goes out. You've seen some areas of the country with fires or severe cold or hurricanes lose power. And so we've got various companies saying, I can't afford to be down with manufacturing. My laboratory, for instance, might have critical experiments going on that if they're down, they're lost. So really mission critical is really growing in the industry. And it's gone beyond the traditional data centers and the hospitals, and it's really encompassing a lot of different. We've had entire universities or other campuses, research campuses, say they want to back up the entire site just because of the reliability concerns over the utility power sources. So.
Good. So it depends. Thank you.
Yes.
Zach, the next question is for you. How do we know when NEC Article 708, Critical Operations Power Systems, comes into effect for a project?
Right. So I think personally, I got stuck on the Article 708 for a while reading it, because it was the first time in the National Electrical Code where it felt like the code was almost, to me, it almost felt like the code was telling you how to design the system, which felt a little awkward. But I think there's a key thing within Article 708 that I think is very important. And it says that an assessment needs to be done to determine the levels of redundancy, as far as like how many layers of criticality that the facility is going to run into. So there's actually another NFPA reference. I believe it's 1500. I've already forgot it. I believe it's NFPA 1500 that has that study and how to perform that study. So if you're at a public entity where you have 911 call center, emergency communication center, first step is to have the security or assessment done on the facility, and then Article 708 for the critical operations power systems will help guide you to the design and installation requirements for the code.
Sure. Okay. Thanks, Zach. All righty, Brian, the next question is for you. Can medium voltage be considered for standby generators?
The answer is yes. And we're seeing more and more applications for medium voltage generators, both at the 5 kV and 15 kV, simply because the amount of power that's being required on some of these sites and the distribution lengths. You don't want to be running 480 volt, your typical generators, 1,000 feet across a campus or a large data center hyperscale situation. So if you can't locate the generator next to the load, there's some benefits to having a central generator plant, and medium voltage can be great for that. And they are appropriate for standby applications, and most of the vendors can give you the information on their ability to start up and their runtime.
Okay, got it. Zach, the next question is for you. Can you address fault current and arc flash with closed transition?
Right, and I think the question for closed transition transfer switches. So I'll just speak on the available fault current. So I think where that question is coming from is because we're making before breaking on a closed transition transfer switches, the question is do you have to consider both the utility available fault current and the generator fault current at the load terminals should you have a fault condition on the load side of the transfer switches, to essentially would be pulling both sources of power. So personally, I haven't found anything that sticks in code that tells you have to consider both. We'll typically consider both in our power system studies as a best practice. And most times we're finding that the rating of those transfer switches can withstand both fault currents, but it's certainly a consideration to look at both incoming fault currents on the load terminals of your transfer switches when you are specifying the closed transition transfer switches.
Sure, great. Thank you. We do have time for only one more question. And Brian, this one's for you. This is kind of an explanation here. Can you give more detail as to what you mean by generators being kilowatt limited? And you mentioned considering the kilowattage of the generator before considering the kVA. And can you expand on that one?
Yeah. So when you look at a building that you would design, a load that you would design, you obviously are going to understand or come close to understanding what the power factor of the building is. Most buildings that I work on these days are 0.9, 0.95 power factor. They're very efficient. That's because you're using electronic ballast for the lighting. You've got VFDs on all the mechanical equipment. Everything's very efficient. So you're approaching unity power factor, and in fact, you can go over unity power factor with some data center applications. The generators are hanging on, and we talked about the generator, the engine, and the generator, right? Because there's two components of that. when I started out, I calculated the kVA like you would for a transformer size when I was a younger engineer and said, okay, I'll take 1,000 kVA generator, not realizing that, or 1,000 kW generator, you get confused between the two. So you really, the generator part of the engine generators, for some reason, they still continue, the industry use a 0.8 power factor for the sizing and the rating of their generator of electricity to your loads. So you can't use the kVA because they'd have to upsize the generator portion of the engine generator to meet a higher power factor. And they can do that as well. You might need a bigger, to ask them, not a standard matchup, but a mix and match between the engine and the generator.
All right, got it. Well, like you mentioned, we could talk about this all day. Unfortunately, that's all that we have time for. So I'd like to wrap up by thanking these extraordinary subject matter experts, Zachary Carter and Brian Renner, for sharing their extensive knowledge of power in mission-critical facilities. And I'd also like to thank ABB and ASCO for supporting this education session. Before we go, we need your feedback to improve future education sessions. A brief survey will pop up on your screen as soon as this webcast ends. Please take a few seconds to complete it. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, thank you for joining us, and we'll see you again at the next session. Goodbye.